Okay, so let's jump right in with a question for you. What on earth does a super smart chess program, one that can outthink a grandmaster, have in common with one of those little robot vacuums that just tries to, not fall down the stairs? The answer is actually pretty deep. Turns out they're both what we in the AI world call agents. And each one is on a mission to figure out and master its own little world, its own environment. One of those worlds is a 64-square grid of pure, cold logic. The other? It's the chaotic, unpredictable mess that is your living room. And that's exactly what we're going to break down today, this relationship between the AI agent and its arena. Because if you really want to understand an AI, its smarts, its blind spots, its future, you have to start by understanding the world it lives in. So, here's the plan. We'll start with the basics, the agent and its arena. Then we'll take a tour through different kinds of worlds, from the perfectly predictable ones to worlds ruled by chance, then worlds filled with other players, and finally, the big one, our own messy reality. All right, first up, before we can talk about all the cool stuff, we need to get on the same page with the language. And in AI, the two most important words you'll hear are agent and environment. So, what's an agent? An agent is the one doing the work. It's the thinker, the actor. It could be a bit of code, a physical robot, even us. The key thing is that it senses its world, with a camera, a microphone, whatever, and then it acts on that world using its tools, whether that's wheels, a robotic arm, or just typing words on a screen. And the environment? Well, that's the stage. It's everything outside the agent where the action happens. And as you're about to see, the rules of that stage, the type of arena, completely changes the difficulty of the game. So let's start in the simplest arena imaginable, a world where everything is known, everything is predictable. This is the realm of pure logic. No surprises, no curveballs. This idea goes all the way back to the ancient Greeks. Aristotle's syllogisms were all about this. If your starting facts are true, like Socrates is a man, then your conclusion is absolutely 100% guaranteed to be true. It's this kind of rock-solid, deterministic thinking that forms the foundation for AIs in these perfect, predictable worlds. Think of it like a super simple GPS problem. You know all the roads, you know all the distances. The solution isn't some clever strategy. It's just a list of steps. Go here, then go there. Because the world is completely known and predictable, there's no need for a plan B. You just follow the script. But don't make the mistake of thinking predictable means simple. Take a look at this number. That's 500 quadrillion. It's a ridiculously huge number. And it's the rough number of possible board positions in a game of checkers. Even with simple rules, the scale can be just mind-boggling. And that's the power of AI in these logical worlds. In 2007, after nearly 2 decades of crunching the numbers, a team of researchers completely solved checkers. They proved that if both players play perfectly, every single game ends in a draw. And AI totally mastered a world with 500 quadrillion states. Wild. Okay, but let's be real, most of the world isn't a checkerboard. So let's level up and add a bit of fog. What happens when our agent has to deal with pure chance? And what if it can't even see the whole picture? A fantastic way to think about this is comparing chess to backgammon. In chess, the world is deterministic. I move my knight, I know exactly where it lands. But in backgammon, you roll the dice. Suddenly, the world is governed by probability. The outcome isn't certain anymore. We've just jumped from a deterministic world to a stochastic one. Now, let's switch gears and compare chess to a card game like bridge. In chess, the world is what we call fully observable. You see every single piece on the board. But in bridge, your opponent's cards are a complete mystery. This is a partially observable world. The agent has to make its best guess based on incomplete information, trying to figure out what it can't see. So how on earth does an AI navigate through this fog? It uses the powerful tools of probability. This is what lets an agent weigh its options, update what it believes when new information trickles in, and figure out the best move even when the world is fundamentally uncertain. All right, let's throw another wrench in the works. What happens when the environment isn't just random, but it's filled with other intelligent agents who are thinking, planning, and trying to outsmart you? Now we're in what's called an adversarial environment. This is the world of competition, of strategy, of trying to get in your opponent's head. And to survive here, AI has to use game theory, the mathematical study of how and why we make decisions in strategic situations. The classic prisoner's dilemma nails this perfectly. Put yourself in Alice's shoes. She has no idea what Bob is going to do. So she thinks, okay, if Bob rats me out, I should definitely rat him out too. 5 years is better than 10. And if Bob stays silent, my best move is still to rat him out. I'd get 0 years instead of 1. So no matter what Bob does, Alice is better off testifying. And Bob, of course, is thinking the exact same thing. So they both testify, and they both get 5 years, even though they could have gotten just 1 year each if they'd both kept quiet. That's strategy for you. All right. We've seen perfect worlds, uncertain worlds, and strategic worlds. Now it's time for the final boss. Let's see how all of this comes together in the ultimate arena for any AI, the real world. You see, the real world is the final exam because it has all of these challenges at once. It's partially observable, our sensors have blind spots, it's stochastic, random things happen all the time. It's dynamic, the world keeps changing even while you're trying to make a decision. It's continuous with a basically infinite number of possibilities. And of course, it's crawling with other agents, people, cars, you name it. This is exactly why robotics is so unbelievably hard. A robot has to move through actual physical space, and it's constantly getting fuzzy data from its sensors, and its motors never do exactly what they're told. That gap between a perfect computer simulation and our messy reality is just enormous. Which brings us to Shaky, a true pioneer, an AI robot from way back in the 1960s. Look at its list of actions. They seem almost laughably simple, right? Go, push, climb. But the challenge wasn't just programming the idea of go. It was getting Shaky to actually roll across a real room with bad lighting, uneven floors, and glitchy sensors. Just getting it to do one of these things in the real world was a monumental achievement. And that's where we'll leave it. AI agents have become gods in their digital arenas, from the perfect logic of checkers to the insane strategies of modern video games. But making that leap, from mastering those clean, simplified worlds to truly mastering our complex, chaotic, and unpredictable one, that's still the ultimate frontier. And figuring that out is what the future of AI is all about.